Hi guys, welcome to our next section for arithmetic. If you are new to the channel, before you start the lesson, I encourage you to go to the link in bio to download the full roadmap of our series for visualizing. Let's get to lesson 1. Ratios. This lesson establishes the fundamental principles of ratios, a concept listed as a core topic in our arithmetic curriculum. In professional mathematics, a ratio is far more than just two numbers. It is a statement of relationship that allows us to scale, compare, and distribute resources with absolute precision. What is a ratio? A ratio is a mathematical comparison of two or more quantities that belong to the same category or kind. It serves as a descriptor of how much of one specific item exists relative to another. Consider a scenario where you have 2 apples and 3 oranges. We define the ratio of apples to oranges as 2 to 3. It is important to remember that a ratio does not tell you the total number of items in the universe. It describes the internal balance of the group you are observing. It is a tool of pure comparison, stripped of any magic or complexity. Ways to write ratios. In academic and professional environments, you will encounter 3 primary notations for ratios. They are mathematically equivalent, and being comfortable with all 3 prevents confusion when the notation changes in more advanced problems. The colon form, written as 2:3. The word form, written as 2 to 3. The fraction form, written as 2/3. Clarifying these notations early ensures that you will not feel overwhelmed when the format shifts in different mathematical contexts. Simplifying ratios. The process of simplifying a ratio is identical to the logic used in simplifying fractions. To express a relationship in its most basic form, you must identify the greatest common factor, or GCF, and divide both terms by that number. Example: if we have a ratio of 8 to 12, we observe that both numbers can be divided by their GCF, which is 4. Dividing 8 by 4 gives us 2. Dividing 12 by 4 gives us 3. The simplified ratio is 2 to 3. The governing rule is that as long as both sides of the ratio shrink or grow by the same factor, the fundamental relationship between the quantities remains unchanged. Ratios versus fractions. A common point of confusion is treating ratios and fractions as the same entity. While they look similar, their definitions differ significantly. A ratio compares 2 distinct parts to each other, such as 3 boys to 5 girls. In this case, the total group consists of 8 parts. A fraction represents a part of a single whole. For example, 3/5 means 3 parts out of a total of 5. Distinguishing between these two concepts early is vital. Failing to do so can lead to significant errors in algebraic logic later on. A ratio compares. A fraction represents a portion of the whole. Equivalent ratios. Equivalent ratios are created by scaling the relationship up or down. To maintain the integrity of the ratio, you must multiply or divide both terms by the same non-zero number. If we take the ratio 2 to 3 and multiply both sides by 2, we create the equivalent ratio 4 to 6. If we multiply the original terms by 5, we create the equivalent ratio 10 to 15. In this field of study, the consistent pattern or relationship matters much more than the specific numbers used to express it. Ratios in real context. Ratios are not abstract concepts. They are the governing logic behind various real-world scenarios. We use them to define the balance between boys to girls in a classroom, red balls to blue balls in a set, distance to time and travel, or cost to quantity when determining value. Ratios are present in nearly every aspect of measurement and comparison. Solving basic ratio problems. Solving ratio problems is a mechanical, step-by-step procedure. When you are asked to divide a total amount into a specific ratio, follow this logical sequence. Example: divide the number 18 in the ratio of 2 to 1. Calculate total parts. Add the components of the ratio together. 2 plus 1 equals 3 total parts. Determine the value of one part. Divide the total sum, 18, by the total number of parts, 3. 18 divided by 3 equals 6. Therefore, every single part in this problem is worth 6 units. Distribute the shares. Multiply each side of the original ratio by the value of one part. 2 parts multiplied by 6 equals 12. 1 part multiplied by 6 equals 6. Verification: the resulting shares are 12 and 6. This process is purely mechanical and requires no guesswork. Common errors to avoid. As you work with ratios, you must remain vigilant against these typical mistakes. Partial simplification: you must always perform the same operation on both sides of the ratio. Mixing inconsistent units. You cannot compare different units directly, like meters and centimeters, until they have been converted to a common unit. Confusion with equations. Ratios are comparisons of value. They do not solve themselves like algebraic equations. Exercise module. It is now time to apply these standards to your own work. Please focus your attention on the first 4 challenges. Question 1. Simplify the ratio 10 to 15. Question 2. Generate an equivalent ratio for 3 to 4 by multiplying both terms by 3. Question 3. Divide the total of 20 into a ratio of 3 to 1. Question 4. Solve a cost and quantity problem. If the ratio of red balls to blue balls is 2 to 5, and there are 10 red balls, calculate the corresponding number of blue balls. I strongly encourage you to continue through the remaining exercises, numbers 5 through 20. Consistent practice with these core mechanics, without the use of calculators, will ensure you have a firm grasp of the topic. Summary. In summary, a ratio compares 2 quantities of the same kind. They can be expressed in multiple notations, simplified using the greatest common factor, and scaled as equivalent ratios. Remember that while ratios compare parts to other parts, fractions compare parts to the whole. Mastering these relationships is a key building block for the arithmetic that follows. You have now mastered the art of comparing quantities using ratios. You understand how to simplify relationships, scale them up, and divide totals into precise shares. But comparison doesn't stop with simple numbers. What happens when we want to express one quantity as a part of 100? How do we calculate discounts, interest, or population growth in a way that everyone understands? In our next lesson, Lesson 2, Percentages, we will take your knowledge of ratios and fractions and apply it to one of the most common and powerful tools in modern mathematics: